Why space shuttles don't burn up during re-entry. Have you ever gazed up at the streak of a meteor burning across the night sky and wondered why space shuttles don't meet the same fiery fate? Re-entering Earth's atmosphere is one of the most dangerous phases of a spacecraft's journey. Hurtling at speeds of 25,000 kilometers per hour, space shuttles face a torrent of friction with the atmosphere, generating temperatures hot enough to melt steel. And yet, astronauts on board emerge unscathed, greeted by safety on Earth. How is this possible? Buckle up, because today we're diving into the brilliant science, revolutionary engineering, and human ingenuity that makes safe re-entry a reality. From heat shields to precision angles, this is the untold story of why space shuttles don't burn up upon their return. When a spacecraft re-enters Earth's atmosphere, it essentially collides with the air at hypersonic speeds. Picture this, traveling at 25,000 kilometers per hour is not just fast. It's almost 20 times the speed of sound. Moving that quickly through the atmosphere compresses air in front of the spacecraft, generating tremendous heat. Temperatures can soar to over 1,500 degrees Celsius, hot enough to vaporize nearly any material if unprotected. These extreme conditions pose two critical challenges. Heat management. Without a way to deflect or absorb the heat, the spacecraft would disintegrate. Structural integrity. The immense pressure and turbulence during re-entry could cause serious damage to the shuttle's frame. Without proper precautions, the fate of the spacecraft would mirror that of a meteor breaking apart in the atmosphere, turning into little more than a trail of fiery particles. The secret to surviving these intense conditions lies in the groundbreaking technology of heat shields. Unlike meteors, which have no protection, space shuttles are built with specially designed thermal protection systems. These systems act as a barrier, absorbing and redirecting the enormous heat generated during re-entry. For the space shuttle, this protection comes in the form of thousands of unique heat-resistant tiles. Made primarily of silica, these tiles are about as tough as they are lightweight. Silica has remarkable heat insulation properties, so effective that you could hold one side of a tile with your bare hand while the other side is being blasted by a blowtorch. It's these tiles that ensure the shuttle's aluminum framework stays cool despite the blistering temperatures outside. Each tile is a masterpiece of engineering, customized to fit specific areas of the shuttle. The belly, which experiences the most intense heat, is covered in tiles designed to take the brunt of re-entry forces. Meanwhile, areas exposed to less heat may have tiles with slightly different properties. Together, these tiles form the shuttle's primary defense during its fiery plunge. Physics alone dictates that materials, no matter how advanced, aren't enough to guarantee survival. The angle and trajectory of re-entry play a massive role in ensuring thermal protection is effective. Imagine throwing a stone into a pond. If the stone strikes the water at too steep an angle, it plunges straight into the depths. Likewise, if the space shuttle enters Earth's atmosphere at too steep an angle, the heat and pressure from the rapid descent could overwhelm its defenses. Conversely, if angled too shallowly, the stone skips across the pond's surface, never sinking. Similarly, with a shallow re-entry, the shuttle risks giving off the Earth's atmosphere altogether, becoming stranded in space. For this reason, every re-entry is a finely choreographed descent. Missions are planned to achieve the perfect trajectory, neither too steep nor too shallow. Space shuttles descend gradually, reducing friction at strategic intervals. Rather than free-falling, they glide through the atmosphere, which helps dissipate heat more evenly. To better understand the brilliance of space shuttle re-entry, it's helpful to compare their journey to that of meteors, fiery streaks that burn up before ever reaching Earth's surface. Meteors enter Earth's atmosphere chaotically, with no control over their speed or angle. Without protective coatings or thermal barriers, they ignite almost immediately. Friction breaks them apart, leaving only glowing trails of debris in their wake. Space shuttles, on the other hand, are precisely engineered for a controlled descent. The heat tiles protect them from incineration, while their aerodynamic, wedge-like design directs airflow away from critical areas. This combination of strategy and shielding allows astronauts to defy the same forces that destroy meteors. Behind every shuttle re-entry lies a mountain of planning, calculation, and collaboration. Engineers spend years perfecting the thermal materials, testing them in simulated re-entry conditions. Every tile is inspected, repaired, and replaced as needed before each mission. Precision here is non-negotiable. Just a single damaged tile could create a weak point, jeopardizing the entire mission. Astronauts, mission control specialists, and engineers work as one cohesive unit to execute re-entry flawlessly. Timing, trajectory, and descent rates are controlled down to the second. Even under the most harrowing conditions, this teamwork ensures the spacecraft withstands the heat, stress, and turbulence. The Space Shuttle program marked a breakthrough in solving re-entry challenges. Before this, early space capsules like Apollo relied on ablative heat shields. These shields worked by intentionally burning away, carrying excess heat with them. While effective for one-time use, ablative shields couldn't support reusable spacecraft. The Space Shuttle changed everything. Its reusable heat tiles were revolutionary, enabling the craft to launch, orbit, re-enter, and land multiple times. This innovation opened the door for more practical and cost-effective space exploration. For astronauts inside the shuttle, re-entry is nothing short of surreal. They feel the vibrations of atmospheric turbulence coursing through the spacecraft. Outside, plasma, superheated, glowing gas, engulfs the shuttle in a fiery orange cocoon. To them, it's a spectacle of nature, science, and engineering working in harmony. Though they trust the heat shield to protect them, the stakes are always high. Astronauts' lives depend on the technology and calculations developed by ground teams. Returning through Earth's atmosphere safely isn't just a scientific achievement. It's a testament to human determination to explore the unknown. The success of the Space Shuttle program paved the way for modern spacecraft. Companies like SpaceX now use heat shields made of advanced materials, enabling vehicles such as the Dragon capsule to survive re-entry and support rapid reusability. These advancements are vital as we push further to Mars and beyond. In the future, we may see even more sophisticated solutions. Plasma shields, ultra-light thermal materials, and advanced deceleration techniques could redefine what's possible for spacecraft returning to Earth or landing on other planets. So why don't space shuttles burn up during re-entry? It's all thanks to a blend of cutting-edge heat shield technology, calculated re-entry strategies, and an unwavering commitment to perfection. This isn't just a story of survival, it's one of triumph, of humans defying nature's most daunting challenges. Next time you see a meteor flashing across the night sky, remember the countless innovations that keep astronauts safe on their own journeys home. It's through this ingenuity that we continue reaching for the stars. Space calls to us, and thanks to the marvels of science and engineering, humanity is ready to answer.